Hi everyone. Today, I'm going to tell you a bit about VMware's brand new service-defined firewall solution. We just announced the availability of the solution, and we couldn't be more excited to show it off for you today. In this presentation, we'll showcase how the service-defined firewall mitigates a real attack on an application. But before we dive into the demo, let me tell you a little bit about what the service-defined firewall actually is. With an infinite number of threats out there, it's a losing battle to try to identify and eradicate each one individually. In addition to threat hunting, we need to focus on reducing the attack surface of our environments to help level the playing field. We developed the service-defined firewall as a way to reduce the attack surface of applications within the walls of the network perimeter. It takes a very different approach to firewalling than what you're probably used to with a traditional perimeter firewall, because frankly, it solves a very different problem than a traditional perimeter firewall solves. Perimeter firewalls are designed to keep bad stuff out of the internal network. Because the traffic they filter originates from unknown hosts out there on the internet, they're limited to a network-centric understanding of traffic, namely layer 7 packet inspection. Inside the network perimeter, we need to take the attitude that the bad stuff has already found a way in. Our job is to limit the damage the bad stuff can do before we can identify it and respond to it. When it comes to shrinking attack surface inside the network perimeter, in order to mitigate attack vectors like lateral movement, we aren't dealing with unknown hosts like we are at the perimeter. We're dealing with our own applications, our own hosts, and the services that our own developers are creating. As a result, we can have much deeper contextual understanding of the traffic that is moving east-west within our environment. An understanding that is grounded in looking at traffic through the lens of the application that created it in the first place, because ultimately, it's applications that we care about protecting. We can build an understanding of what known good application behavior should look like. How do we expect the hosts and services that make up our applications to behave? Which processes do we expect to see running on them? What traffic do we expect to see resulting from those processes? As you'll see in the demo, the service-defined firewall is designed to build this picture of known good application behavior and dynamically turn that visibility into policies that enforce it. These policies can be enforced both at the network level, creating microsegments around the application, and they can be enforced at the process level, within the host themselves. The service-defined firewall can adapt policies as the app changes over time as well. And furthermore, it can enforce these policies consistently across the entire environment. By doing so, the service-defined firewall is creating a least privileged or zero trust security posture for the entire application. By defining policy for both the network and process level of the app, the service-defined firewall helps mitigate threats that leverage multiple attack vectors, as you'll see in just a minute. To accomplish all of this, the service-defined firewall is delivered through the deep integration of two of VMware's products, NSX Data Center and App Defense. In order to bring this to life, let's look at an actual attack on an application that is secured by the components of the service-defined firewall, NSX and App Defense. Okay, so the app we are attacking is a basic 3-tier web application, complete with a web tier, app tier, and DB tier. The website is running on Drupal and is back-ended by a MySQL database. First, I'm going to attack the app without the service-defined firewall components in place. The only defense the app has is antivirus running on the servers. Of course, as an attacker, I don't know any of this. So the first thing I'm going to do is investigate what's running on the website by doing some recon. I run a quick script on my attacker machine, in this case a Kali Linux box, to determine how the content of the web app is being delivered. In this case, I see that the app server is running Drupal 8. Then I use Searchsploit, which is a freely available exploit finder, to see if there are any known vulnerability exploit combinations that will allow me to compromise the app server. As you can see by the list of results, yes, there are indeed some exploits that exist that we can leverage here. Next, I use the exploit and run a quick script to initiate a reverse TCP connection, which allows me to gain access to the app server. With shell access, I have the ability to execute code directly on the machine. We can confirm that the host has been compromised by verifying from the command line what the system's hostname is. Using the same exploit code, I immediately disable the antivirus on this machine. The first thing any attacker will do once they compromise a machine is disable any known security tools running. With the AV disabled, I run Mimikatz to dump the user account's hash and credentials on the app server. Now that I have these credentials, I can use a pass the hash attack to gain access to the database server of the application. And after I log into the DB server, I can now upload, install, and run a crypto miner to start making some money. Okay, let's recap for a second. One of the main reasons I was able to successfully compromise this app was because I was able to exploit the app server over port 8443, a port that is open by necessity so the app can communicate with the internet. Once I gained access to the app server, I was able to immediately turn off the AV protection. From there, I dumped the credentials from the app server, which gave me free rein to move laterally within the network using a pass the hash attack in order to gain access to the database server. Once I had control of the DB server, I was able to install my crypto miner software and exfiltrate my Bitcoin. So now, let's start layering in the components of the service-defined firewall solution in order to lock down my app. We'll start by enabling app defense, which will begin to learn and understand how the app should behave. With app defense running, we start to see application behavior show up in the dashboard as the product starts to discover how my app is working. These behaviors are really just the processes running on the host that make up my app. Because app defense is embedded directly into the vSphere hypervisor, the behaviors we see are coming directly from the VMs that host my app without the need to push additional agents to those VMs themselves. For each process, app defense runs the behavior through the app verification cloud, which provides a general reputation score for the binary. As the name suggests, the app verification cloud is designed to verify that the behavior of a given application is, in fact, known good behavior. In addition to reputation feeds, the app verification cloud leverages VMware's expansive footprint to analyze known good app behavior across millions of workloads. This analysis informs whether a given app's behavior looks normal or not. With the picture of known good behavior established for our application, we can visualize our app's topology. From within the visualization, we can drill into the dependencies of the different tiers and understand what normal network traffic looks like for the app as a whole. This visibility is instrumental in determining what process-level behavior should or should not be allowed by the policies we create. Here we can see that the app tier normally communicates to several public IP destinations as part of its execution. We can also drill into the individual processes and see the command line arguments that the process is executed with, the hashes associated with a given process, and of course, the network connections that the process is making. This deep understanding of what talks to what will become important when we are ready to create network security or microsegmentation policies to lock down the app. Here we see the current NSX distributed firewall rule table. Take note that there is nothing for the host we've compromised, meaning we are providing no segmentation for the application from an enforcement standpoint. Once I'm content that app defense has learned all of the known good network and process level behaviors of my app, I can put the system into protected mode. When I do this, you can see that I have the option to create network security rules that will be implemented and enforced in NSX. By moving my app into protected mode, I'm telling the system to create network and process level rules that will ensure that only the known good behavior is allowed to take place. In the case of the network, these rules are microsegmentation policies, which will lock down network communication to a zero trust model for the entire app. In particular, notice this rule that restricts communication between the app server and the DB server to port 3306. In the case of process level rules, I've configured the system to alert when deviations are detected, rather than outright block the deviant process from running. Okay, so now let me put on my attacker hat again and try to reproduce the attack from before. I can still disable AV on the app server, and I can still dump the credentials from the app server to try my pass the hash attack. I can also still access the web tier and get shell because, as we mentioned before, the app needs to be able to communicate to the internet. But this time, when I try to pass the hash, I'm blocked by the microsegmentation policy governing traffic between the app server and the DB server. You will notice here that the communication is now blocked between these two servers. Even though I can't log into the DB server like I could before, I can still find the credentials for the database from some files that exist on the app server. By using that username and password, I can easily recon the SQL database and grab whatever important customer data I can. Once I have that confidential data, then I can kick off a ransomware program to cover my tracks. Okay, let's recap again really quickly. Here's our app, but now you can see that I have microsegmentation policies deployed between my tiers, and I have App Defense watching on each server, in addition to my AV agents. Remember, App Defense is actually embedded into the hypervisor. There's no App Defense agent running on these servers, though the icons make it look like there is. I gained access to the app tier the same way I did originally, through port 8443. I disable the AV agent and dump the credentials, but when I try to pass the hash, I'm blocked by the microsegmentation policy this time. So instead, I deploy some ransomware to cover my tracks and remove any trace of our unauthorized access to the app server, because I might as well cause a little mayhem while I'm in here. While the microsegmentation policy prevented me from being able to carry out my ideal attack, I was still clearly able to manipulate the app server by exploiting the operating system. And here's the result. Okay, let's reset the environment really quickly. This time, I'm going to put App Defense into block mode, instead of just having it alert when it detects a deviation at the process level of the app. As you can see, while I was able to manipulate the app server in my last attack, App Defense was actually sitting there watching everything I was doing and alerting on it. The alerts show every step of the attack and every command I ran. With App Defense in block mode, when I try to execute commands that deviate from the normal process level behavior of my application, the product will prevent the commands from executing. We can even see details on the Petya executable, which is the encrypting ransomware that was used to target the Windows system. Now, let's run the attack one more time. This time, as you can see, I'm not able to get shell on the app server. I'm also unable to disable the AV agent. I'm pretty much stuck, and the only thing I can do is close up my laptop and go make a sandwich. For completeness sake, let's do a quick recap of this last attack. You may notice that my green icon on each server is now a lock rather than an eye, indicating that App Defense is actively blocking deviant behavior. As usual, I entered the app server via port 80, but this time when I attempted to get shell, I was denied. I also tried to disable the AV agent on the machine, but that was blocked as well. My attack essentially died on the vine. A quick look at the App Defense console also shows that the blocked commands were logged and alerted on, so that my security team is aware of what took place. So there it is, the service-defined firewall in action. To sum it all up, you got to see how App Defense and NSX work together to establish and verify the intended state and behavior of an application, then orchestrate and deploy policies to enforce that intended state and behavior. In the end, the service-defined firewall solution was able to shrink the attack surface of my application and mitigate both a lateral movement attack and a code execution attack. Simple as pie. In all transparency, VMware has been working on solving this problem for a long time. When we launched NSX back in 2013, we introduced the concept of microsegmentation, but our solution was limited to layer 4 port blocking. Over the years, we've steadily built in the ability to define microsegments based on additional context, including attributes like user identity and layer 7 app awareness. With the launch of App Defense and the introduction of adaptive microsegmentation in 2018, we laid the foundations for the service-defined firewall solution that you just saw. There are actually a few reasons why VMware is uniquely positioned to deliver this kind of solution. Let's take a quick look at each of them. The first is our intrinsic position within the virtualization layer of the environment. Because the service-defined firewall's components are built into the vSphere hypervisor, the solution is able to get complete visibility and control of the services and traffic that make up applications, all without the need for additional agents. The second ace up our sleeve is the App Verification Cloud. The App Verification Cloud streamlines the process of establishing known good app behavior by applying machine learning and human intelligence to the data generated by our massive footprint. Applying machine learning to understanding and defining good behavior is a relatively unique application in the security field. Most security vendors that leverage machine learning are using it to attempt to characterize bad behavior. But machine learning works best when applied to enormous data sets of predictable scenarios. There are countless examples of good application behavior in the world, and that is what we are training our algorithms on. Finally, VMware is first and foremost a software company. The service-defined firewall is delivered entirely in software, and it would be impossible to achieve the same results if it weren't. Not only does our software-based approach allow us to enforce policies consistently across heterogeneous workloads, but it also allows us to leverage a distributed architecture. One firewall deployed everywhere. It would be financially and operationally infeasible to deploy a physical firewall in front of every host in your environment. And with that, our presentation has come to an end. I hope that everyone enjoyed the demo and has a good grasp on what the service-defined firewall is all about now. If you're interested in learning more about the types of attacks that the service-defined firewall can mitigate, check out the Threat Mitigation Report produced by Veridin, a security technology validation company that helps vendors and businesses alike validate their cybersecurity defenses. You can find the report on the service-defined firewall page of www.vmware.com. along with a lot of other great assets and information. Thanks so much for tuning in.